And so the next speaker is Benjamin Greenhagen, who's going to talk about unmixing lunar surface compositions using near-infrared and thermal infrared data sets, connecting orbital and laboratory measurements. So you're good to go, Ben.
Great. Thanks, Tim. Can you hear me?
Yes. All
right. Yeah, and thanks for the shout out in the previous talk as well. I will talk about those samples in just a little bit. Okay, so yeah, so this work, we're going to talk more about near infrared and thermal infrared, but we're going to step back just a little bit to what we can see from orbit and what we can do in the laboratory to understand those orbital data sets. So Chris just gave a really nice description of all of the variations inside the pyroxene and olivine compositions. For this talk, we're going to assume that those don't exist, at least for right now. And we're going to talk about ternaries of plagioclase, pyroxene, and olivine. And so these are two summary plots from earlier work, Lucy 2006 on the left and Cahill 2009 on the right, showing where lunar soils on the left in these blue shades fall on this three-component ternary through measurements of return to Apollo soils. And then on the right, the different gray shades are rock lithic fragments within return to Apollo soils, showing that the soils themselves, these ground up material, does not show the same compositional range that the lithic rock fragments do. And then also on the plot on the right are some red diamonds that show central peak compositions determined from near infrared spectroscopy. And one of the things we want to work on in this work is how we can get better constraints on composition by including thermal infrared, which has different dependencies on composition. So in the thermal infrared, we have typically, for the moon, I should say, we've been using the Chris-Johnson feature as our indicator of silicate mineralogy. The plot on the lower right shows for different compositions what emissivity spectrum in a simulated lunar environment look like. And this broad peak is the Chris-Johnson feature. It shifts to shorter wavelengths for things like plagioclase and longer wavelengths for more mafic things like olivines. The highest sensitivity that we have with this value is the plagioclase mafic abundance. So if you look at this ternary in the upper right-hand corner, I've now basically colored it to an approximation of what the CF would be doing across this space. And you can see you get the greatest color difference on that plagioclase to olivine line, the troctolite line, than you do in the other spaces. And we want to use this phenomenon that we see in thermal infrared spectroscopy, along with the really great constraints on mafic compositions you can get from near infrared spectroscopy. So getting very detailed information about what the pyroxene to olivine ratios are specifically. So if you imagine having two compositional potential lines, these plots in the bottom right hand are showing what you get from the thermal infrared in the solid line and the near infrared in the dashed line, and you can get a very tight constraint. So that's the thesis behind this technique, and it's something that we've been working on for a number of years, and it's been funded by LDAP to do this work. Oh, and I should say before I go on here, for this study, we're using Diviner and multiband imager data. Those are the two data sets we're using, but this can apply generally. So moving forward, if you have a great mission like Lunar Trailblazer that can get both that near infrared spectra and the thermal infrared spectra at the same time, you could solve this simultaneously with coincident measured data, and that would be absolutely fantastic. Okay, so really what we're trying to do here is go from this plot in the upper left-hand corner, which is the Chris-Johnson feature values measured by Diviner, to this plot in the lower right-hand, which is the modeled plagioclase abundance. And to do this, Paul Lucy came up with this algorithm. And you can see the flow chart on the right. This is pretty complicated, but there's just a few basic steps. The first one is to take our Chris-Johnson feature values and correct for space weathering effects. That's the top part here. After we do that, we use a series of equations to combine the Kaguya multiband imager existing mineral abundances and the laboratory Endmember values to produce a new plagioclase abundance map that I just showed. This is then iterated with Lunar Prospector GRS to validate it and stretch it so that the units are accurate. and then we bring that back in to a second iteration with the mafic abundances to get what the final olivine and pyroxene abundances are. So if you're interested in taking a deep dive into this, that there's a link to the paper here. If you just Google Lucy Diviner 2021, the first thing that shows up is this paper, and inside it there's also links to these data products. So our CF map I just showed is on Zenado there. All of these green box products are also there. So go please check it out. And it is just more than mineral maps that we've been doing with this. In particular, we did a significant improvement of the space weathering correction. Originally was published back in 2017. There's now a new version that takes into account iron abundance as well. And a discovery, I should say, of this work was that if you do a decorrelation between Kristiansen feature value and FEO, you get really some of the most interesting spots on the moon come out as either dark or bright anomalies. So dark anomalies have a iron deficiency, and they include the plagioclase and silicic anomalies. And bright anomalies would have an iron excess, and they include areas like the olivine-rich areas around Moscoviense, and also, interestingly, lunar swirls. So this data product is also available there too. Thanks, Tim.
4 minutes, Ben.
Got it. So flipping over to the other side, the lab measurements. So this is what Chris just mentioned. We have 49 mixtures that we created across this ternary to do the laboratory measurements on. We used Miyake-jima anorthite, which is the most lunar-like anorthite. And then we used a forsterite and Tanzanian enstatite. And we are focused just on the finest size fraction for this work. And all the measurements were made in our simulated lunar environment chamber at APO. This is a work I just described last year, so I'm going to go through this pretty quickly. This is what our updated ternary looks like if we assume our updated Endmember values, similar to what has been shown before and published previously. If you include all 49 mixtures across the ternary, you get something that looks pretty different. But the good news is that if you go across this ternary in different directions, they're actually very smooth trends, nearly linear trends, except for when you get to the very high olivine abundances. And so that's something we wanted to look at a little bit more. And in particular, because of the method we used a constant lamp temperature. And so the samples we're measuring, which we're measuring in thermal emission, were actually physically different temperatures for these measurements. So we wanted to make sure that that wasn't a factor. So after we took 2 years to measure 49 spectra, we measured 49 more in considerably less amount of time. And we got essentially the same answer. So this nonlinearity that's associated with the plagioclase to olivine, the troctolite line, is not a temperature effect. So that is good to know. And then I should say that this is actually inconsistent with some results we did on Apollo soils by varying temperature. So something is going on between these pure minerals and more real geologic space weathered samples that will be a future investigation. So in summary, how we can take this back to the mineral map data is that in both cases, we have linear trends. So we will be able to update the algorithm, but honestly, we expect fairly minimal differences because of the work that we already did tying things to the Lunar Prospector GRS and to the near infrared. But if there are differences, the area they are going to occur is in that troctolite corner. And with that, I will stop.
Thanks a lot, Ben. Questions for Ben? Chat. We'll say that's a very nice flow chart.
It is. I'll go through a link to the data locations into chat too, so people can go right to them. They're open access, so you don't have to have any subscriptions to get them.
Question from Mahesh: are agglutinates messing things up in the Apollo samples?
Yeah, it's probably something related to the agglutinants or the fact that the Apollo samples actually have quite a wider range of particle sizes than what we were looking at. We really only included the finest grain, whereas the Apollo samples we measured had the full size distribution up to, I think, 200 microns in them. And so those can create little thermal shortcuts on these these types of textures we're looking at. So agglutinates, opaques, different grain sizes, all of those are going to be complicating factors.
Imagine all the visible albedos of all of your samples were probably much brighter than the Apollo samples.
They are.
Sorry.
Yep.